Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to be here today. The topic of the talk is creating secure execution environments without secure hardware. So let me start with a brief motivation. We all know this. There are vulnerabilities and attacks pretty much in every software layer in the system. You have bootkits in the BIOS. Unfortunately, there's a new trend. Started with UEFI. You have rootkits in the OS, old news. Malicious JavaScript in the browser, old news again. With this kind of a situation, it's rather obvious to ask, how do we establish a root of trust for computing on a device that is potentially untrusted or compromised even, right? So as a starting point to answer this question, we begin with the observation that the minimum hardware resources that you need for any computation are CPU and physical memory or RAM, right? So then the question is it possible to verifiably set up CPU and memory controller state so that no malicious code can tamper with the execution of a given executable that, for the purposes of this talk, I'll call the target code, right? So pictorially, what's happening is we have the hardware underneath, we have a potentially malicious software stack, and there is this target code. What we'd like to do is to set up essentially this execution environment that we will call the Untampered execution environment, or UEE, for the execution of the target code, so that even if the rest of the software stack is malicious, this target code can execute unmolested. Right. So what we need for this approach is for it to work on legacy systems. So which means that we cannot rely on hardware extensions. So we want a software-based approach which can be deployed on both current and legacy systems. So with that in view, we said let's take the following functional approach, right? So let's modify the CPU and memory controller state to set up the UEE. We saw earlier that these are the minimum hardware resources that you require for any sort of computation. Let's go ahead and generate an attestation that proves that this UEE is in fact correctly set up, and the target code binary is in fact unmodified. And then let's go and invoke this target code inside this UEE. Okay. Pictorially, what we did is we generated, well, so part of the screen is cut off here. We developed what's called a verification function, which is a combination of a checksum code and a SHA-1 hash function. And what that verification code does is it first sets up this UEE by setting up the appropriate CPU and memory controller state. Then it computes a checksum, both over the state itself and over this checksum code and the hash function. So in other words, the checksum code is self-checking, right? Then it sends the checksum to an external verifier. You'll see in a minute what this verifier is. It computes a hash. The SHA-1 hash function is going to compute a hash of the target code, send the hash to the verifier, invoke the target code directly, and since the target code is in fact getting invoked directly from this code, which has already set up the UEE, it is inheriting that execution environment directly, right? So the target code is executing inside the UEE, or at least we hope so. Okay, what's the problem here? The problem is that
I have one question.
Yes.
So if I compare the previous picture, right, the picture in the previous slide,
Right.
to, for example, how SGX, Intel SGX does it, right?
Right.
There I think the checksum code is in the hardware. So
I mean,
the hardware executes it. So they don't have to worry about that.
This whole thing is the hardware.
In the hardware. So essentially, they still have to do a checksum, but they don't have to worry about the integrity of the checksum code itself.
Yes, and I mean, they don't even have to do a checksum. It's sort of axiomatic that you trust the hardware. It's like another example is TXT, right? When you set up a DRTM, you don't care about.
But they have to do a checksum because you don't trust the communication, and somebody can intercept the code.
They can intercept the code, but this state that is set up, right? So this figuratively, this wall is some state that is set up inside the CPU to create an enclave. That state, you just trust the CPU that it will do the job for you. It'll protect the right memory regions,
Yes.
all that you just assume it'll happen. So they don't have to worry about that part of it. But you're right. I mean, they do still have to do attestations across the communication channel because they don't control that. But inside the CPU, they're okay. Whereas we have nothing, right? So we essentially have nothing to rely on. That's the.
So who's the verifier?
Yeah, that's coming up. Okay, so as we just talked about, the attacker could very easily forge the checksum. So how do we detect such forgery, right? So we said, okay, let's try to use time as a side channel to detect attempts to forge the checksum. So the key idea is that this checksum code will execute slower if the attacker, in fact, tampers with its execution to forge the checksum. Okay. So what's the security property, right? So as we saw pictorially earlier, the checksum code is going to take the UEE state as well as the verification function binary image as inputs, right? Therefore, given the existence of the timing property, and we'll see in a few slides why the timing property, or at least why we expect the timing property to hold. So given that the timing property holds, the correct checksum, which is obtained within the expected time, will provide the guarantee that, first of all, the UEE is correctly set up, and secondly, that the verification function code itself, the binary image, is unmodified, right? So based on these guarantees, the verifier that obtains the correct checksum within the expected time can conclude that after the checksum is computed and returned, all the actions subsequent to that event will be performed by an unmodified verification function that is executing inside a correctly set up UEE, right? So now to answer your question, the verifier is, as you see in this picture, is in fact a device in a USB stick form factor, right? So it's running some variant of the ARM processor. I'll tell you what in a few slides. And what it does is it communicates with the untrusted host across the USB bus. Inside the untrusted host, of course, you have this verification function that consists of the checksum code, the SHA-1 hash function, and you also have the target code that you want to execute. So the protocol works as follows. At time t1, a nonce is sent to the untrusted host. The nonce is used as an input to the checksum code, which computes the checksum. The checksum is sent back to the verifier at time t2. Because of the timing property, the verification is declared to be successful if t2 minus t1, the time elapsed for the computation, is less than the expected time, and the checksum equals the expected checksum. The nonce is again fed as an input to the SHA-1 hash function, which computes the hash of the target code as a function of the nonce, returns that hash, and then finally invokes the target code for execution. Right, so this is the protocol. So that sort of completes the overview of the system. So before I get into our two prototypes, to achieve this overview, I want to point out that this problem is actually extremely hard to do without any kind of hardware support. In fact, we visited Intel Research very early in this prototyping effort to ask them if they had some insights. And one of the things they told us is, beginning about the early 90s to mid 90s, they in fact worked on these kind of timed hash generating functions. And the goal was to detect attempts to copy softwares or at least prevent them. And then they gave it up as being too difficult for a general purpose CPU. They said, yeah, we can do it for small 8-bit CPUs, but for x86 it's just too hard, and they just gave it up. So that was pretty much the stage at which we started this research. So with that, we'll talk about Pioneer first, and then the next prototype called Outpost. I'll start with the assumptions. So yes?
I have a question, right? How do you know what is the expected time?
We know what the expected time is because the verifier is executing the checksum code by itself. So it knows what
but it may not get scheduled as often depending on the CPU utilization.
The thing to realize here is that the checksum code is running on bare hardware without anything in the middle. All the interrupts are turned off. There is absolutely nothing between the CPU and the code. The code, once it takes over the CPU, just runs. Nothing is going to stop it. Nothing is going to preempt it.
I'm also confused by a few things here. So the nonce already ensures non-replayability and all that.
Right.
So then what is the timing that is, what is it that the timing that you
let me answer briefly now. Maybe it becomes clearer as we analyze the attacks. So the trouble is that, let's say we are generating a checksum over the verification function, right? So the attacker is free to modify that function as they want. So they modified it. Now, what they do is, when you read a modified location to put it in the checksum, the attacker simply substitutes the modified value with the correct value. And so finally the checksum is correct. How do you detect this? So the claim of the timing property is that if you do such attacks, the checksum computation is going to take longer, and therefore you will detect this.
Actually, maybe you answered this, but one thing that's not very clear to me is actually what prevents an attacker from doing a checksum on the actual code. And can I compute the correct checksum?
Yes, we'll get to that.
Then replace the code.
We'll get to that. Okay, so there is an attack called the memory copy attack that in fact does what you say. So the attacker runs a malicious checksum function that computes the checksum over a copy of the good expected verification thing, and simply, since the malicious code is already in control, I mean, there's nothing you can do about it. So yes, that attack does exist, and we will analyze it. I'll show you in a few slides. Okay.
But that's, the timing is nothing to do with that.
The trick is to make sure that any attempt to perform an attack like that increases the execution time. So the construction of the checksum code has to be done in such a way that the timing property holds when this attack is done. And we'll see how we finally achieve that.
Do you make assumptions about the hardware on which the attacker lives?
Yes, right here. So we assume that the verifier knows the hardware configuration of the untrusted host, mainly the CPU make and model, because we would like to know the CPU clock speed and instructions available, things like that. System bus speed, not so important, especially in the second prototype that I'll show you. Also, we have assumptions about the communication channel itself, so we want to make sure that the response, the checksum that we're getting, is actually coming from the host we're checking, not from somebody else, right? So that's one assumption. The other assumption is that this host is not simply forwarding the challenge to another faster host and getting, colluding with it to compute the checksum. So these are all assumptions. Single CPU assumption. For x86 especially, we assume that the untrusted CPU has 64-bit extensions. You will see why this is important in a few slides. And finally, we have assumptions on the target code. It is self-contained, so which means that obviously it shouldn't be making calls to the untrusted code, because then all this effort is of not much use. And then it executes at the highest privilege level with no interrupts or exceptions. Right? Again, this is a fairly strong assumption, which we will relax in the next prototype that I'll show you later in the talk. Okay, what is the attacker model? Of course, as you saw, the attacker has full control of the software stack. Also, the attacker doesn't modify the hardware, and particularly doesn't overclock the CPU, doesn't swap the CPU for a faster one, no malicious peripherals. The attacker does not modify memory using DMA. And for x86 in particular, the attacker does not modify what's called the system management mode or SMM handler. Okay, so with that introduction, here's a set of attacks we analyzed. So we said, what are all the different ways people can subvert the system? So broadly classified into 4 categories. We have attacks to force the checksum, one of which Sriram, we discussed in answer to your question. We have attacks to tamper with the execution of the target code. So basically, you preempt the target code when it's executing and try to gain control, so you can do what you want. You can try to speed up the checksum computation by various kinds of optimizations. And of course, there is the pre-computation and replay attacks. Right. So for the purposes of this talk, I'm going to focus just on 2 of these attacks in the interest of time. So I'll start with what's called the memory copy attack. Before that, I need a few properties of this checksum function to be able to logically argue why the attacks increase the time of computation. So the first property is that the checksum code is an iterative function. And what we try to do is that each iteration generates a certain amount of overhead, so that the total overhead, the total time overhead, increases linearly with the number of iterations. Right? Obviously, we need the implementation of the checksum function to be time optimal. This is an open problem that needs proof. That in fact, we do have a time optimal checksum function implementation. In the paper, we have a reasonably structured argument, in fact, even somewhat formal, that says why we believe this to be true, but it still needs proof. I mean, it's not proved. The checksum function is strongly ordered. The idea here is that if you evaluate the operations in a different order with a very high probability, it will result in a different checksum. So an example is computing something with an alternate sequence of exclusive ORs and adds. So if you change the order of operations for a fairly large subset of the domain, the output is going to be different. Of course, the checksum is a keyed checksum, and the way this is keyed is the nonce is used to seed PRNG whose output is incorporated to the checksum, right?
So this is what will prevent parallelism. A client to evaluate the checksum
yes.
parallel.
Partially, yes. Partially, this will prevent parallelism. Yes. Okay. So the memory copy attack. What is the memory copy attack? So during correct execution, what happens is the checksum code is going to compute a checksum over the image of the verification function, right? What happens in the memory copy attack is, of course, you place a malicious checksum code somewhere else in memory. Mind you, this is all physical memory, all RAM locations. And then the malicious checksum code simply computes a checksum over the copy of the unmodified verification function, right? So there are essentially three variants of this attack. The first variant is that the malicious checksum code is in fact sitting somewhere else in memory, which means that in the correct execution, the program counter is going to move through these regions, whereas in the malicious execution, the program counter is going to move through those regions, right? And because of that, the attacker's program counter will be different. I mean, it will contain different values, right, during this execution. The second variant is you push the checksum code. You push the copy of the correct verification function to other regions in memory. You execute from the regions you're expected to execute from. So here, as you see, the data pointer is going to be different. The third variant is, of course, that you change the positions of both. So as you see, both the program counter and data pointer will be different. Okay, so it appears intuitive that let's just put the program counter and the data pointer in the checksum. Because the attacker has to forge one or both of these values, depending on the kind of variant of attack used, to generate the checksum, we're going to say that this forgery is going to increase the attacker's computation time, right? The trouble here is this only works if you can access the program counter and data pointer as physical addresses, which is pretty much impossible on modern CPUs because you have virtual addressing. So what are the problems with virtual addressing, right? So the trouble is that the same virtual program counter or data pointer values can be translated into different physical addresses, right? And there are at least three variants of an attack of this kind. There is what's called the split TLB attack. So what this does is when a virtual address is accessed as code, it translates to one physical address. If it's accessed as data, it translates to a different physical address. So in other words, the instruction TLB and the data TLB are desynchronized. Okay. There is the option of using data addressing with a constant or register offset. Fairly obvious. You can just add an offset to every data address you generate, and so you can access another memory. There is also the option of using the offset addressing using what's called the segmentation feature on x86 CPUs. Right. Okay, so yes, please.
Sorry, could you go back to the picture?
Right.
Yeah. So pardon my ignorance. I don't know too much about how all this works. But why is it the case that I cannot go and just modify the program itself without actually changing the program counter? Why does it have to be? Why does this malicious checksum code have to be a separate piece of code?
You can.
So there is some checksum code. Why can't I just go modify some parts of it so
Yes.
that I retain the program counter to be exactly the same?
So you have modified the program in place. Now the program is reading itself, right? When the program reads itself, some of those reads are going to touch the locations you have modified because you have modified the program. So how are you going to handle that? Either you can handle that by doing something like this, where you keep a pristine copy and refer to it. So you are unconditionally redirecting all reads to a pristine copy. Or you perform conditional execution, where you say if the current address equals a changed address, then please substitute this correct value for the value you read. So both attacks are possible. And in fact, when I showed the slide on attacks, there is what's called a data substitution attack, which does exactly this. And in the interest of time, I'm not able to cover it, but I'm happy to talk to you about it. And in fact, that attack becomes impossible with the construct we use. Eventually, what happens is you make a change. To counter that change, you put a conditional statement. The conditional statement is another change. To counter that change, you put another conditional, and so forth. So the number of conditional just keeps growing at some point. So when you do the analysis thoroughly, you figure out that at some point you are not able to keep pace with the changes you're making. So this attack is in fact a lot more efficient than doing something in place. That's why we analyze this attack more thoroughly. Okay, so we have those three attacks, and then we said, okay, let's try to figure out how to defend against them. We couldn't come up with any good idea how to defend against the split TLB attack for Pioneer, right? So we just said, okay, we can't do this. Now, what about offset addressing? The challenge here with offset addressing is, especially for the Pentium 4, for which Pioneer was implemented, constant and register offsets can be added to virtual addresses with zero time overhead. This is because Intel, of course, optimized for the common case, and they actually added dedicated address generation units in the load store units. So pretty much you can add any offset to any address, and there's zero latency. This is a problem. I mean, how do we get the attacker's computation to increase in time when there's zero latency for this?
So is the assumption that the verifier can have access to memory addresses that are being accessed? No,
the verifier knows at what physical addresses the checksum function is expected to execute at, and then it will compute a checksum internally based on those values, and it will simply check if the value the checksum returned equals the value it computed.
I see, but there's no assumption that that the code may try to hide the actual accesses it does.
How would the code?
The code can do whatever it wants as long as it actually gives you the checksum that matches yours. Then the attacker wins.
Yes, that's it. The code can do whatever it wants. Yes, we are not, for example, sitting on the system bus and observing every address that goes by to see if. No, we are not doing that. We are sitting outside on the USB bus. All we know is that a nonce send, we get a checksum in return, and that checksum has to match the expected checksum. The time has to match has to be within the time bound we set. That's it. Okay. Another challenge is directly accessing the program counter on x86 is in fact extremely slow, and since the attacker in fact does know the values, the physical memory locations from which we're expected to execute, they can simply replace the read of the program counter with a constant, which is faster, of course. So we hit this wall and we said, this looks sort of close to impossible. So what do we do? So we said, let's try to do the following. Let's say that the correctness of the checksum depends on a sequence of absolute jumps, right? Then if you can incorporate the jump targets into the checksum, indirectly you're getting hold of the PC, because the jump target is in fact getting into the PC and you're putting the jump target in the checksum. So this has promise. The trouble is that the jump targets themselves are constants. I mean, what prevents the attacker from simply replacing the jump target, the read of the jump target, with a constant? So the attack still remains, unfortunately. So for the modification, let's say since the jump targets are constants, what if the jump targets were not constants? What if we replace them with some kind of pseudorandom jump targets? How can we do that? So we said, let's reorganize this checksum code so that it's in 4 blocks, right? And each block is going to generate a jump target as a function of the current checksum value. As you know, the checksum value is a function of the output of a PRNG, and therefore the jump targets that are generated will be pseudorandom, right? And as you also saw, the checksum function itself is strongly ordered, and each of these 4 blocks is going to use a different order of those operations. So the correct order of execution of the blocks is necessary to get the correct checksum with high probability. So based on these two properties, we come to the conclusion that if the attacker in fact does not perform the pseudorandom jumps correctly, with high probability the checksum will be incorrect. Okay, so pictorially, as you see, the blocks, they sort of surroundingly jump around. There's the last instruction is a jump, indirect jump to register type of instruction. So the value is computed. The value of the jump target is computed within the block, loaded into the register, and you simply jump to that, right? So that's how it goes. So this sort of helps us get hold of the PC. But what about offset addressing? I mean, we saw earlier that it can be done with zero overhead, right? What do we do there? So here, there are two variants, right? So either you can use a register offset, or you can use a constant offset. Now, for register offsets, we said, well, you have to use a register. So what if the checksum code simply uses all the registers, all the GPRs that are available? There are 16 of them on this x86 architecture. So let's make sure that all those are kept alive throughout the checksum computation. And so the attacker has to save and restore. So that increases the attacker's computation overhead. What about constant offset? Now, constant offset, there are two ways of doing it, right? So either you can use the segmentation feature, or you can simply use a constant. If you use the segmentation feature, what we observed is for the instruction encoding on 64-bit x86, the instruction length increases by 1 byte. If you use a constant offset, the instruction length increases, of course, by the length of the constant, the size of the constant. So we try to see if we can use this dichotomy to increase the attacker's time overhead. So how do we do this? So what we did is you saw the checksum code being organized as 4 blocks. The first instruction of each block is going to do a memory read. So in fact, it's of the form of add the contents of a memory location to a register. This instruction on the 64-bit x86 is exactly 3 bytes long. Now, as we saw in the last slide, if you use offset addressing, whether it's a constant offset or a segmentation-based offset, the instruction length increases at least by 1 byte, right? So in other words, an instruction of the form add memory register will be at least 4 bytes long. Okay. Now, what we did is we modified the pseudorandom jumps so that each pseudorandom jump will land with equal probability on either the first or the third bytes of a block, right? So what this does is, in the attacker's case, where the attacker is using this offset addressing and its instruction length has gone to 4 bytes instead of 3, about half the jumps will land in the middle of an instruction. And what that'll do is either the checksum itself will be incorrect because the incorrect instruction sequence is getting executed, or more likely there will be an illegal opcode exception at some point in the execution. So pictorially, we have the pseudorandom jumps jumping either to the first byte or to the third byte. This is the correct execution. In the attacker's execution, we see that the instruction length of add memreg has increased by at least 1 byte. So, so when the jump in fact hits the third byte, it's going to land in the middle of this instruction.
So where is the pseudorandomness coming from?
The pseudorandomness is coming from the PRNG, that is that the nonce is seeding. So I mentioned.
It's not specified by verifier or anything.
No,
inbuilt into the system.
The nonce is specified by the verifier. The nonce is used to seed the PRNG. The PRNG is outputting a pseudorandom stream.
How do you guarantee that PRNG is executed correctly?
We guarantee that the PRNG is executed correctly because it's part of the checksum. I mean, it's part of the checksum computation, right? And the output of the PRNG is incorporated in the checksum. So if the PRNG is not executed or is executed incorrectly, the checksum is going to be incorrect. Okay. Okay. But this is not the end of the story. What can the attacker do? The attacker can, of course, modify the pseudorandom jump addresses before the jump, and then change the addresses after the jump so that the correct address does in fact get into the checksum, but the attacker can jump wherever it wants to. But what happens here is, of course, the attacker has to perform these extra computations. So essentially, we are forcing the attacker into a place where it has to perform extra computations, and that slows down the attacker's computation, right? Okay, so that sort of finishes the high-level analysis of this memory copy attack. What you see here is the key observations here are that the defense is extremely specific to the 64-bit variant of the x86 architecture. It is extremely hard for you to do any kind of formal reasoning as to why this attack is not going to work.
Why are you using SHA-1? Where are you using SHA-1?
We are using SHA-1 to compute the hash of the target code before passing control to it.
But I thought that's what the checks. But what is check? I mean, all this plus and is XOR and anything. I thought that was a checksum.
Yes. So there is. Okay. Let me go to the next slide. Yeah. Okay. So we have the checksum code, right, which is what I talked about all this while, which has those properties of alternate adds and XORs, and then we have the SHA-1 hash function. The role of the checksum code is to compute this checksum as a function of the nonce over this and the UEE state, as you saw earlier. The role of the hash function is once the checksum is computed and returned, assuming that the checksum verifies correctly, the SHA-1 hash function is guaranteed to execute inside a UEE, and the SHA-1 hash function is guaranteed to be unmodified. At that point, the SHA-1 hash function takes a hash of the target code, and therefore you can trust the hash that you receive from the SHA-1 hash function. Okay. Okay, so another set of attacks, taking control using exceptions and interrupts. So what happens here is that the attacker simply installs malicious interrupts and exception handlers. The interrupts can be triggered wherever you want, typically during the execution of the SHA-1 hash function, or even during execution of target code, you'd gain control, do what you want at that point. So the obvious solution, of course, is replace the exception and interrupt handlers with verified ones, right? So all of them. So we don't want any malicious, registered interrupt exception handlers. The harder question is, at what stage of the execution of this verification process do we actually replace these interrupt and exception handlers? So you've seen this picture earlier. The order of execution is the checksum code goes first, does the checksum computation, passes control to the hash function, which computes the hash, and then passes control to target code for execution, right? Now the checksum code itself is in 4 units. So there is the initialization code, there's the checksum loop, which we talked about all this while, which does the actual computation. There's the epilogue code, whose job is to put things together before the send function sends the checksum to the verifier, right? So potentially we have 4 places where we can replace the interrupt and exception handlers. So let's analyze them case by case to see where we actually do this. So what's the safest place to replace these handlers, right? If you do it as initialization code, well, the attacker is free to simply skip the initialization code because we have no control at that point. If we do it in the checksum loop, well, these are redundant instructions. I mean, they don't contribute to the checksum. So the attacker simply deletes them, saves time. Bad again. If we do it in the epilogue code, it's bad again because the attacker can simply trigger a debug breakpoint at the entry of the epilogue code, and well, you lose control again. So again, as before with the memory copy attack, this appears impossible. So what did we do? We said, let's try and use the stack for this purpose. So as we know, when a CPU receives an interrupter exception, state is stored in the stack, right? So what we said is, let's keep part of the checksum on the stack. So now, if the attacker decides to trigger an interrupter exception, that part of the checksum is going to get overwritten. So with this arrangement in place, what we can do is we can safely replace all the interrupt and exception handlers after the checksum is computed, but before the checksum is sent to the verifier. Because the valid checksum is still sitting on the stack, and at that point, if you generate an interrupt or exception, the checksum is just gone, right? So that's exactly what we do. So in the epilogue code, we in fact replace all the interrupt and exception handlers with valid handlers, or verified handlers.
But I guess actually, but the checksum code has to be extremely carefully written so that it doesn't actually make a function call or anything like that.
It doesn't
use the stack.
Yes. So let's get there. I'm coming exactly to that. So here is the checksum computation does in fact use the stack. Why does it use the stack? Because we need access to the condition codes register, and on x86, the only way to get access to the entire 64-bit condition codes register is to push it on the stack and then put it in the checksum. The trouble, of course, is that this is going to overwrite the checksum. So we have to carefully manage the layout of the stack in such a way that we can use the stack but there's still enough checksum on the stack so that an interrupt or exception will result in the checksum being overridden. I'm not getting into the details here. If you have questions, we can always talk about it in the one-on-ones. Okay. So even after all these, jumping through all these hoops, there are still several attacks that Pioneer does not address. Yes,
so
please.
The original interrupts are enabled once you send the function finishes. When the target code executes, you have to enable it.
You can re-enable the interrupts, right? So see, we have in the epilogue code, before the send function sends the checksum out, all the interrupts and exception handlers are replaced with verified handlers. Now when the target code gets controlled, it is the verified handlers that are in place. The target code is simply free to replace those handlers with its own handlers and re-enable interrupts and execute.
At that point, those handlers can be malicious. I mean,
those handlers are, remember, those handlers are registered by the target code. So you of course you trust the target code to know what it wants to do, because once you pass control to the target code, and the target code is either malicious or it's it can be exploited remotely as that kind of a thing is outside the problem scope, because the only guarantee we are making is we will set up an environment in which the target code will execute unmolested from whatever is outside the environment. If the target code itself does bad things to itself, well, that's too bad. Okay, so there's a whole list of attacks, that low-level attacks that we didn't take care of. Also, there are a number of limitations of the approach. So first of all, it's a non-portable design, as you saw from the analysis. It is very difficult to know what the best attack is. I mean, we don't even know if we know all the attacks to start with. The attacker overhead is extremely low. In fact, it's approximately 2%. Very easy for somebody to optimize it away, since first of all, we don't have a proof that the implementation is time optimal. There is no architecture independent formal security analysis. And in Pioneer, the verified device that we used was actually another computer. It was not this USB stick. And so people pointed out that how do you trust the verifier? I mean, it's in fact another computer. What if the verifier lies to you? So if a human is involved in the verification process, then that's a problem. Right? So this pretty much was the state of things when we started working on the next prototype, which is called Outpost. Once again, when we got this Pioneer was published, we got feedback from a number of people. They thought we really pushed the envelope quite a bit. But the general consensus at that point also was, well, you guys have pushed the envelope, but this is interesting as a concept, not anything more. I mean, it can't be a practical system. You have all these very strong limitations. And that was pretty much how it was when I wrote my thesis proposal, where my advisor said, all you do is just address all the attacks we know about, and you finish your thesis, right? So then I said, no, that doesn't work, because we have to build a practical system. Otherwise, it's just research. It's not going to go anywhere. So that was the goal with which I started doing the next prototype, Outpost. So here, I'll start again with the attacker model. As you see, the attacker model is much stronger, right? So all we do is we assume the attacker can arbitrarily modify all the software on the untrusted host, all the hardware of the untrusted host functions according to the stated specification. So once again, the attacker doesn't modify the hardware. So no malicious peripherals, no malicious CPUs, for example. The attacker does not overclock the CPUs. So this is the attacker model. A lot of the assumptions that you saw earlier are done away with. We only assume that the verifier knows the CPU make and model. We assume that the untrusted host has wired communication interfaces only. Alternatively, if there is a way by which wireless interfaces can be verifiably disabled. And what I mean by verifiably disabled is if in fact there is a bit in a register that you can set that says, okay, now the wireless interface will not work, and you can take that register and put in the checksum, then it is possible to simply discharge this assumption. The reason this is still an assumption is because we didn't get far enough in the prototyping effort to see if this is actually possible. So it's just listed there as an assumption. Of course, the target code is self-contained. That still holds. Also, the untrusted host has IMMU support. Now, this was an interesting thing because right when we started working on this, Intel and AMD were going very big on their virtualization efforts. So they started putting IMMUs in their hardware. So we said, okay, let's make use of that to defend against ZMA attacks. Right? So in other words, we have things like the AMD IMMU, Intel VTD, things like the AGP guard. So let's start from the beginning again. So we'll start with the problem definition, try to make it more formal so that we can reason our way through the problem rather than doing an attack defense based approach. So what's the goal? The goal again is prevent malicious code from tampering with the execution of target code. Okay, fine. So how does this tampering happen exactly? So there are 3 ways it can happen. So the malicious code can modify the target code image binary, the instructions themselves. It can modify the inputs that are passed into the target code, and it can modify the execution state of the target code as the target code executes. Okay, so we're going to go down this list one by one and see what we can do. So let's build the requirements. To detect attempts to change the target code instructions, you can do simply, you can check the integrity of those instructions before you execute the target code and protect the integrity of those instructions after you've done the check. So you don't have a time of check to time of use type problem. You don't have a race condition there, basically. So what do? You compute and return the hash of the target code before invoking that target code for execution. And you prevent any writes to the target code instructions between the start of computation of the hash and the exit of the target code, right? So this gives you the ability to detect attacks against code integrity. Okay, so how do you prevent number 2 and 3? So which is that the malicious code is in fact executing concurrently with the target code, and it's either modifying the inputs or it's modifying the execution state. So that's preemption, right? So what you do is you force all malicious code to stop executing from the time between the start of computation of the hash to the time till the exit of the target code. So when you preempt everything, pretty much the malicious code is not executing concurrently, and therefore there's no way it can tamper. So, and the challenge here really is that the malicious code happens to be the entire software stack. So how do you preempt the entire software stack? So that's what we'll get into. So to get there, I am going to list a few properties of the hardware which constitute a hardware operational model that we use. So the first one is that concurrent code execution can happen via one of 2 ways, right? So there is either time multiplexing that uses interrupts to change execution context, right? And for this purpose, an interrupt pretty much is any asynchronous or synchronous signal that indicates a need for change in execution. So this is a fairly broad definition that includes everything like hardware interrupts, software exceptions, the virtualization intercepts, etc. I mean, pretty much anything you can think of. The other way to do concurrent execution, of course, is parallel execution. And when we say parallel execution in multiple CPUs, now architecturally we have a number of variants of this. So for our purposes, we'll define a CPU essentially as a hardware unit that is capable of processing a unique or independent instruction stream. Because of this definition, practically what happens is the number of CPUs in the system for us is equal to the number of instruction decoders that are present in the system, right? So this definition again is broad. It covers pretty much every form of parallel execution you can think of: hyperthreading, SMP, SIMD, MIMD, clusters, what have you. Okay, the second property. This one is about how interrupts are an operational model for interrupts. So the CPU supports multiple interrupt sources, right? And not all of these sources are maskable. So the implication is there are some interrupts which simply cannot be turned off. They will always occur. Okay. All interrupt handling is vectored, which means that there is a memory address for every interrupt. There is a memory address from which the CPU fetches the first instruction of that interrupt handler. Now, the address itself can be given in various forms. It can be a fixed value that you write into the architectural specification of the CPU. It can be programmed into a register in the CPU. It can be in a table in memory. All of these variants are possible. Okay. Now, the third property, this is about memory accesses. So memory accesses in the system can originate only from one of 2 sources. One is the CPUs, and the other is from peripheral devices. When I mean memory here, I mean the physical memory, the RAM, right? So RAM can only be accessed via these 2 sources. The CPUs access memory on behalf of the programs they execute. So programs initiate a memory access. The CPU, through its hardware link, actually reads the memory. Devices can only access memory via the DMA mechanism. So there is no other way via which a device can access physical memory, and this happens to be true. I mean, of all the in all the architectures, at least I know of, this is true. Okay, and of course, programs can request devices to access memory on their behalf using DMA. Okay, so we have these three sort of properties, and using this, we will recast those untampered execution requirements. So the first one is preemption. So how do you get preemption? So as we saw earlier, the only way to do concurrent execution is to either have multiple CPUs or use time multiplexing using interrupts. So what we do is for each interrupt source of the CPU architecture, and remember, once you have the CPU architecture specification, you know what are all the interrupt sources the CPU supports. And this is public knowledge, it's listed, it's there, it doesn't change. And what you do is you either disable the interrupt source, which of course works only for maskable interrupts, or you set the interrupt vector to point to verified code, which will work either for maskable or non-maskable interrupts. When you have a multi-CPU system, of course you have to do this for every CPU in the system. Okay? The second one is you want to make sure that each CPU executes only verified code before the hash computation starts. Because if you have malicious code already running on a CPU, I mean, you're not in good shape at that point. So this is the list of requirements for preemption. What is the set of requirements for code integrity protection? Well, you prevent DMA accesses to target code using the IMMU. We saw earlier that the only way peripherals can access system memory or RAM is via DMA. Then what you do is, for CPUs, you don't have to do anything because preemption is already in place before the hash computation starts, and therefore there is no malicious code executing the CPU. So any memory access that originates from the CPU, which originates on behalf of a program that's running on the CPU, is going to be okay. So all you have to do is set up the IMMU. So in conclusion, what is the UEE state? To set up a UEE, all we have to do is, first of all, modify the interrupt vectors and or the interrupt control registers, and set up IMMU state to prevent DMA to a region of memory. Right? So really, going back to the design of our system, all you have to do is checksum these two elements to make sure, or this set of elements, to make sure that the UEE is correctly set up. And if the verifier verifies the checksum, it knows that the UEE is in fact correct. So what we do is, because of the way the requirements have changed, the structure of the verification function has also changed. As usual, you still have the initialization code on the top. You have the checksum code. I mean, this is, I'm sorry about the terminology, this should actually be the checksum loop. So the checksum loop is still in place. You have the epilogue code still in place, you have the send function still in place, and you have the SHA-1 hash function still in place. What's different is you have an interrupt table here. So this is where you will make sure that all the interrupt vectors are pointing to the default interrupt handler, which in fact is the verified interrupt handler. Because it's part of the verification function binary image, it will be verified, it will be checksummed as part of the verification process, and therefore it's a verified interrupt handler. The interrupt table itself will be checksummed as part of the verification process, and therefore you can trust that. Similarly, when you set up IMMU page tables, they are part of the verification function binary image as well, so they will be checksummed as well, so they will be verified. Okay. So functionally what's happening here is that the initialization code is really setting up the UEE. It's going to, for each interrupt on each CPU, it is going to either disable the interrupt or vector the interrupt to point to this default interrupt handler. It is going to set up the IMMU page tables to prevent writes to the verification function binary image in memory and to the target code in memory. So the checksum code, as usual, is going to generate the checksum as a function of the verification function memory image, the nonce, and the UEE state. So once again, what are the attacks? So if you think about it, all attacks against the scheme can be classified into two, right? Either the attack is executing in the context of the code of the verification function, right? Or it's executing outside that context. If it's executing in context, then you have two kinds of attacks: the memory copy attack, which we saw earlier, and the data substitution attack, which Nishant we talked about. The attacks that execute outside the context, of course, have to use interrupts to switch context. So that can be anything, debug breakpoints, virtualization intercepts, what have you. Okay, so let's again analyze the memory copy attack. Again, the same picture. What's the key to notice here is that the attacker uses two copies of the checksum code during its execution. There is a malicious copy that executes. There is a copy that's sitting up there, a pristine copy that's sitting up there that the attacker refers to. I mean, this is a given, right? This is the definition of the attack. So based on that, let's do the following. Let's build a verification function that fills the CPU's L1 data cache. Okay? Let's make the checksum function, the checksum code, right, self-modifying. So what self-modification in this case means is each iteration of the checksum code modifies a design-dependent number of add and subtract instructions. And there are add and subtract instructions in the code, and a design-dependent number of these instructions are going to be modified. What they're going to be modified to, each of these instructions is going to be modified into an add or a subtract instruction with equal probability. Okay? Now let's analyze the memory copy attack in the context of this construction. So the first observation is the malicious checksum code can either be self-modifying or it need not be. Right? So let's assume that the malicious checksum code is self-modifying. What happens here? The malicious code writes to the L1 data cache as part of the self-modification. Obvious? The malicious checksum code is going to incur L1 data cache misses because of these writes. Why is this the case? Because the correct verification function image is filling the L1 data cache. The attack code is writing to its code locations, remember? And those code locations are distinct. They are in distinct physical memory locations, distinct RAM locations from the correct verification function image. Therefore, these are two different physical memory locations, so some part of the correct verification function image is going to be evicted when the attacker self-modifies. Okay? And then there is an overhead of the L1 cache miss penalty, which is of the order of tens of CPU cycles. Okay. Let's say the checksum code is not self-modifying. The attacker's checksum code is not self-modifying, in which case the attacker has now to do conditional execution. Why is that? Remember, we said the self-modification is going to change an add or subtract instruction into an add or subtract instruction with equal probability. So the attacker has to figure out whether it has to execute an add or subtract, and it can't do that beforehand. It has to do that at execution time. So the attacker has to perform conditional execution, and then the attacker incurs a branch prediction penalty for each self-modifying instruction approximately half the time a conditional executes. Why is this the case? Because each self-modifying instruction can be an add or a subtract with equal probability, which means that the branch predictor, no matter what its construction, can only predict the output, can only predict the direction of the branch with a probability of 50%. So what is the time overhead here? It's simply the branch misprediction penalty, which in modern CPUs is equal to the pipeline length.
So what we have is that the design itself makes the checksum code self-modifying. That's the design.
Yes.
And the replacement uses, I guess, some random number generator to replace it with an add or subtract instruction.
So what happens is you know that the output of a PRNG is incorporated in the checksum, right? So we can simply use bits from the checksum, which are in fact pseudo-random, to select whether to change an add or subtract into an add or subtract. So we just pick one bit, and based on the bit decide if you want to change it to an add or subtract.
But I guess what I'm wondering is that if that depends on the PRNG, then how can you calculate an expected checksum value?
Because you can run the checksum yourself, right? So you know you're the verifier, you know the nonce, then you do the computation.
So when you do the computation, you have to exactly execute all of these
Yes.
things, including the replacements.
Yes. You exactly just run the checksum code. Just run the correct checksum code exactly.
So in this case, why isn't the actual checksum computation also incurring these overheads?
Good point. In fact, because of shortage of time, I cannot discuss that, but I'm happy to talk to you about it. Let's see, the actual checksum code does not incur these cache misses because it's using exactly one copy, right? So there's a checksum code, and it's part of the correct verification function image. It is computing a checksum over itself. It is the same set of physical memory locations that are both in the instruction cache and in the data cache. Therefore, when you do a self-modification, you write into the L1 data cache. When you will get a miss in the L1 instruction cache, but what happens is the CPU will forward the data from the L1 data cache to the L1 instruction cache, and that happens without any time overhead. I mean, this is again an optimization for the common case on most modern CPUs, because you don't want cache misses, right? So it's really that why it doesn't work. So there's also another possibility that the attacker could in fact compress the correct verification function, right? So because we said it fills the L1 data cache, so you compress it, and well, you gain some space. The trouble here is now you have to decompress. Every time I access that image, the attacker has to run a decompression function to give me the correct value. So that incurs a time overhead. Again, we can talk about this attack in great detail. And the third interesting detail is, why don't we also fill the L1 instruction cache? Why only the data cache? This is again a bit of an involved question. So again, I'm going to skip it for now. So here's a high-level comparison. So in Pioneer, we had a non-portable design. As I showed you, Outpost has a portable hardware design that is based on a hardware operational model that holds across pretty much every commodity architecture I know of, right? And as you saw, both the analysis and the memory copy attack, the definition of UEE state, all of these things are architecture independent. Difficult to know what the best attack is in Pioneer. Here we showed you that there are only two classes of attacks, type 1 and type 2. So you can enumerate and analyze the attacks exhaustively and come up with the knowledge of what's the best attack. And in fact, there's an exercise we did undertake, and one of the things that we do in this exercise is the time overhead that we compute is based purely on architectural events. So for example, we will say that there is an L1, excuse me. So we will say that there is an L1 data cache miss, and the L1 data cache miss is going to take n cycles. We are not going to take into account the fact that the attacker may have to run some extra code to do that. So because we don't know, at least we should not predict what the attacker's code is like. So we'll simply take the fact that the attacker's code incurs an L1 data cache miss and use that as a time overhead and nothing else, right? So again, this is something we can talk about offline. There's no architecture independent security analysis. We do have a formal security analysis that is architecture independent. There's an untrusted verifier. We have a trusted verifier now in a USB stick form factor. And finally, we have addressed pretty much all the attacks that Pioneer is vulnerable to. Right? Implementation. So the prototype was implemented on an AMD system. The verifier is pretty much an ARM processor in a USB stick form factor. And we implemented one type 1 attack and one type 2 attack. The type 2 attack is essentially a virtualization based attack. And the reason for this is that because a lot of people were extremely skeptical that hardware virtualization would simply defeat the technique. So we said, let's just implement it and see what happens. So here are the results. In the no attack case, of course, you have zero overhead. In the memory copy attack, the overhead is 15.2%. This is just compare this with the 2% for Pioneer. For the virtualization attack, the overhead is roughly 50%. Okay. So there's a whole bunch of things, of course, that I've not been able to go through here, both design and implementation and formalism. We can take those offline. There's later work. I'm going to skip through this. So I'm going to conclude pretty much by putting on the table what I'm trying to do currently.
I have one quick
Yes.
question. So we can read about both these systems. I mean, Pioneer, I know there is an SOSP paper.
Right.
Outpost also there's an SOSP paper. Or what?
No, Outpost is unfortunately not published yet.
So Outpost is what we're doing at IBM.
Oh, well, Outpost is work I did at IBM,
I see.
and it exists as a technical report at this point.
I see.
Okay, so the problem we see in a cloud and also mobile settings such as BYOD or bring your own device is that there's a shared software stack that is processing data flows belonging to different entities. So you can have different tenants in the cloud. You can have the enterprise and personal for BYOD type things, right? We all know this. I mean, software contains vulnerability, including 0 days. So what happens is that a malicious data flow can simply exploit these vulnerabilities in the code, create an attack, so that shared code is now attacking another data flow. That's of greater interest to us. So what do we do here? So I think what has to be done pretty much is you have to have security controls in every layer of the software stack that provide isolation at the level of individual data flows, not at the level of process or VM boundaries that we commonly know today, which are built on top of OSs or hypervisors. It has to be within each execution context. I mean, it has to be within an OS. Application data flows have to be isolated within a VMM. Data flows have to be isolated within an application. Data flows have to be isolated. That's the requirement today, I think. These data flow isolation controls, of course, are going to be embedded in. So you have something for the OS, it's going to be embedded in the OS, and the OS has vulnerabilities. And even if somehow you manage to build these data flow controls so that they are themselves free of vulnerabilities, you still have the problem that if the OS is compromised, these controls, the execution of these controls could be tampered with. So you need some form of isolation for these controls. The challenge is to provide this isolation while at the same time ensuring that the controls will be able to govern the execution in the rest of the system. Right? So the isolation is one way, and that makes it harder. Okay. The third requirement, I believe, is it is necessary to verify that the controls themselves are in fact executing untampered, and they are enforcing the policy specified in the data flow correctly. Why is this important? Because in a cloud, you want the tenant to know that your isolation is in place and their policies are being implemented. You want the enterprise to know that the user who's having enterprise data on his personal cell phone has the necessary isolation in place on his cell phone and the enterprise policies are being complied with. So there are plenty of challenges here. How do you achieve performance efficient isolation of data flows in commodity systems? I mean, there's plenty of related work here. Most of it, in fact all of it, refers to special systems that have been built or systems which have low performance. I mean, not practical. So this is a challenge. How do you isolate these controls? How do you place a control inside an OS that is vulnerable and still isolated from the OS? At the same time, allow the control to monitor and prevent actions of the operating system. So that's another challenge. The attestation itself is a challenge. I mean, what is an attestation of correct execution and policy compliant operation of these data flow isolation controls? I don't know the answer to this. And then how are these attestations to be verified? I mean, we know code attestation had a lot of promise. The verification was a problem. It turns out that to maintain a database of all kinds of hashes or all permutations of hashes becomes prohibitive very quickly. So how is this attestation to be made scalable? It has to be automated because you can't expect a human to look into the attestations of all those controls on every single machine that's running in the cloud. It has to be integrated into network security management platforms because that's where the automation comes from, right? Finally, if we are to talk about security, I believe we have to have formal specifications or what I call sufficiency conditions for all of the above. We have to know that here are the sufficiency conditions for achieving these, and here's why we meet these sufficiency conditions. If you don't have this, then you have nothing, which is the state today pretty much. Then how can the attestation data, which is returned by these policy enforcement, be used by these controls? How can this data be used to in real time to detect the violations of policy within a very large system like the cloud, like a data center, right? And via integration with these kind of network security platforms. So very hard challenges, plenty of work for all of us. So that pretty much concludes my talk. Thank you.
One question I have is that, do you think your design point that you make no assumptions about the hardware is a good one, or actually do you think on the other end is actually something like Intel SGX, which makes so many assumptions about the hardware? Right? Do you think actually that you can make some assumptions and reduce the number of problems you have to solve?
I think a software-based solution, I mean, I'm partial to this, so my answer is going to be colored. I think a software-based solution is a good one for two reasons, right? So one is the generality of the solution. The second one is if we find an attack against the solution, a software-based solution can be fixed fairly easily. I mean, we had this problem with the TPMs, right? The collision resistance property of SHA-1 was broken. People could not update the TPMs without physically changing the TPM. And the same problem may arise in something like Intel SGX, because that's a fairly complex architecture. I mean, even the architecture is complex. Now think of the implementation, and the implementation is in microcode, most of it. And what happens if now you find vulnerabilities in the microcode? Well, you can update the microcode, but then that gives you an avenue for attack. What if the attacker simply exploits that to load malicious microcode? And that's happened too. You can, in fact, exploit the microcode update facilities to upload malicious microcode in spite of all the digital signatures and stuff. So yeah, so I mean, I think a software-based approach is better. Where hardware can help is it can make it easier to construct a software-based approach. So one example is, I said we want to verifiably disable wireless interfaces, right? So which means I have to read a value in a register somewhere. Now, let's say that register is sitting, way down somewhere on the PCI bus. It probably takes me hundreds of cycles to get to that register. I can still hide that latency because all I have to do is I have to schedule that instruction in the right place and then wait for the right number of execute the right number of instructions to fill those hundreds of cycles of latency. And then once the answer comes back, I can put in the checksum. The trouble is for several hundreds of thousands of iterations of the checksum, I'm probably going to read that particular value a very few times, and that creates an avenue for a probabilistic attack. So on the other hand, if it's made easier for me to read that value with lower latency, I can do this design in a much easier way. I think that's where the hardware support should come.